For our project, we wanted to look at the differences between different trajectory generation methods and see how some are better than others in specific ways. So to start, we implemented a linear interpolation method, a cubic, quintic, and septic polynomial method, trapezoidal method, and a spline method. All of these were implemented in slightly different ways and are better for some scenarios and better for others. So to start, we can look at our cubic polynomial. If we generate a trajectory, we can see that it maps a path between the 2 points, and each of those blue dots represent one space that the inverse kinematic solver will go to at some point. And this can be done in joint space or task space, so this is joint space. And we can look at that for other methods as well. If we were to look at a quintic polynomial, for example, in task space and joint space, it would look pretty similar except for the graph that shows up at the end. So in this graph, we can see up here the position, x, y, and z being plotted in their positions changing over time, the velocity changing over time, and the acceleration of each of the degrees of freedom changing over time. Specifically with quintic here, we can see that the position, velocity, and acceleration are all continuous over the whole time frame, and specifically it looks like acceleration here is a cubic polynomial, which means that it's continuous through jerk. Looking at other methods, we can do trapezoidal, which is specifically better for reaching its maximum velocity for as long as possible. You see how it gets to a higher speed in the middle, and when we look at the graph, it will reach these maximum velocities either positively or negatively for as long as possible. These 4 methods, the cubic, quintic, septic, and trapezoidal, are all really good at doing point-to-point interpolation, so just going from one point to another. The spline, on the other hand, is much better at interpolating between many different waypoints. So we can look at that here, where I just added about 5 waypoints to go to. And as it traverses, we can see that it will go between all of these points while maintaining some amount of continuity. Specifically in this example, I think one of these points makes it discontinuous, but we can see that all of these points get traversed too, and it does that maintaining continuity up through acceleration. So on a physical robot, it wouldn't have any problems on the motors. Specifically, one thing we wanted to do with this was analyze how good some of these trajectories are. So this file here actually runs 50 iterations of generating a trajectory to see how long it takes, and it plots those. So if we run this, we can see that our cubic in task space and joint space are relatively quickly to run. Quintic, slightly longer than cubic. Septic, even longer than that. And trapezoidal is actually the fastest computationally to compute out of all 4 of these. We don't analyze splines in this for time, because for splines we're interpolating between more points than these other methods. But we can see how increasing the order of the polynomial does increase the amount of time it takes to generate each trajectory.